Thank you, Eric. All right, so I'm delighted to be here to share with you some of my work in visible light communication and how to get wireless connectivity through the lighting system. Want to start out by thanking Eric and for inviting me to be Jubilee, to submitting my nomination as Jubilee Professor, and for organizing the seminar for me. I want to acknowledge my collaborators on the work that I'm presenting today, PhD student, well, graduated PhD student Mohammed Noshad, and current PhD student Jay Lian at UVA. And this work was partially funded by the NSF in the US. All right, so let's start at the beginning. So optical communications, I think if you're here, maybe it means that you know and love already optical communications. Well, it comes in many flavors. I've worked in all of these areas, so you'll recognize the fiber here for long haul systems, for backbone systems, and for metro systems. Then we have what's called free space optics, so building to building or laser-based point-to-point communications using device kind of like this. I have one just like that in the lab. And then we have opportunities to use laser comm for deep space and satellite. So these are very traditional notions of optical communications that we've seen really for many years. I want to talk to you about something a little new, visible light communication. So the idea here is to use the lighting system itself for communication. And why do we want to do this? Well, it turns out that an increasing proportion of the data communications, the wireless data communications that we use, is indoors. Last year it went up to 80% indoors, and yet the Wi-Fi system that we have is woefully limited. Right? So what are we going to do? We need to find alternatives, and adding more Wi-Fis, more base stations doesn't help because they compromise each other. They interfere with each other. The reuse isn't possible. So then the other motivation is to note that communications requires a transmission of energy from infrastructure to user. And frankly, we're already transmitting energy from infrastructure to user in the form of light. Okay? So let's just use what we're already sending. All right, so let's think about applications where this makes sense. Now, this isn't a technology that is going to necessarily be used for every application, but it has been proposed for specific applications where there are issues with the current technology. So imagine this auditorium here where everyone sitting is, or this auditorium here, if you were all trying to download video, okay? Say if it's the same video, then it's broadcasting, but different videos, say my talk is so boring, you gotta do something else, then what happens? That the Wi-Fi system can't keep up. Nobody gets any bandwidth, right? So that's a significant problem in environments where people do want to have that connectivity, not necessarily in an auditorium like this during a lecture, but say during a class, in a classroom where students are working on projects and such. The other potential application is in an airplane where you already have, the little light right on top of your seat. Why not use it directly for communication? Then there's open office environments, hospital environments where Wi-Fi is seen as a health hazard, as a security concern, and as a potential interferer for equipment. So no Wi-Fi in hospitals usually. And this is one outdoor application that's very interesting, is vehicular technology. Now what I've drawn here is communication from the street lamp to the car, saying there's congestion ahead or whatever, but they could be communication from vehicle to vehicle, or from the street lamps down to the cars. Imagine that. I would love this. Now, you go into a parking garage and the lights tell you where that last parking spot is. And we really need this, right? So we can use the lights to do this. So what has made this possible, why haven't we been doing this all along, then might come to mind, is that that new technology of these LED light fixtures, LED lamps, so lamps that are made of using arrays of LEDs that have really wonderful properties. They're very bright, they have low cost, long lifetime, they're eye safe, and because they're cost effective, there's a movement to replace these fluorescent type lights with LED lamps. And LEDs have been used for communications for decades. So your remote control is an LED. So we can now use the light for both lighting and communication because the lights are LED based. Right? So there's two types of technologies for white LEDs. Clearly, street lamps don't use white LEDs necessarily, but phosphor-based is a blue LED that then shines through a phosphor process to make it white. And a trichromatic LED is particularly interesting because there's three LEDs within each LED, which is each lamp, that then has three different colors that can be modulated separately. All right, so let's talk a little bit about the advantages and some of the challenges, right? So there clearly, if there are no advantages, then we won't do it. If there's no challenges, then there's no fun. So some of the basic advantages I've already talked about, that it's safe, that it's secure. Oh, I haven't mentioned security. If I want to communicate inside a room with no windows using light, then no one outside that room knows what I'm saying. Now, when it's a presentation like this or a classroom, maybe it's not so important, but I bet the NSA would be very interested. So. Maybe I should say nothing more about that. No interference to RF systems. So we're not saying let's do this instead of that. We can do this and that because they don't interfere. We can add to what's already being used without compromising what's already being used. So the signal from a communication point of view is typically high power. We tend to not be SNR limited. So, and that's very nice. It's environmentally green. So, and I don't just mean when we use green lights. When we use white lights, it's environmentally green because we're already using the lights. And of course, there's a potential for a huge spectrum, and I'll talk more about that because that spectrum isn't automatic. We have to really work for it a little bit. So, some of the challenging problems are listed here, and I'm going to talk to you about some solutions, some research that we've been doing in this area that really address all of these except for the last one. So the LEDs have low rise times, especially the fluorescent LEDs have very limited bandwidth because of the low rise time. Connectivity, we want to be able to put these receivers on little dongles that connect directly to this. And in fact, all of our phones have cameras, so we already have optical detectors that we could perhaps employ. Multi-user support, clearly dimming. We'll talk about dimming. So the nice feature about these new LEDs, lighting, is that unlike fluorescence, it's very easy to dim. And so for some applications, you would want to change the light level. And we want to be able to communicate even with different light levels. And some technologies work, some modulations work better than others for that. Shadowing, so here I am trying to download my movie and I lean under the desk and all of a sudden I'm under the shadow and I don't have direct line of sight to my lamps. So I have to be able to communicate in those environments. Flicker, is when the lights turn on and off quickly in your eye, in the way you can see it, and that's a problem because it's actually a health hazard. It can cause migraines, and occasionally it can cause or trigger epileptic fits and such things. So we really want to avoid flicker. So that's something that we need to concern ourselves about with the, again, with the modulation. And then the last one is the uplink, because the technology that we're talking about is infrastructure to user, so it's a downlink, uplink. You have to use a different technology. We don't imagine that we would necessarily use the lamp, the same visible LED for an uplink. You might use infrared uplink or use a Wi-Fi system for the uplink, since most of the big data needs are for the downlink and not the uplink. So we're going to do all of this in 30 minutes. Okay, so I'm a communication theorist. I want to know about the channel. So here's what we, this is what we have. This is for the indoor channel. The indoor channel is typically worse than the outdoor channel. We have a room where we have multiple LED arrays. These arrays, well, I'm going to call these luminaries that have multiple LEDs on them. And then we have possibly different receivers. And a receiver might be a laptop with a little dongle with a little photodetector on it. And so we have line of sight paths from an LED array then to the photodetector. But we also have unwanted components, potentially unwanted interference component from other LED arrays, or multipath effects from reflections off of walls, off the floor, wherever, right? So that's been studied quite extensively, and impulse responses tend to look like this. Well, you have a fairly sharp response from your line of sight. And then you have this longer tail that's, that can be due to other LED arrays, other luminaries, or from reflections, or combinations of these. So that's what your impulse response typically looks like. When you are shadowed, what we mean is this peak goes away. And this is your COM link right here. Okay, that's a shadowing circumstance. So you need to be able to transition from having this type of impulse response to having just that. Okay? So we're going to model the impulse response in our work using these mixture of Gaussian shape here. And this sigma is going to come up in some of the plots, so you'll know that's kind of how bad that multipath is. Okay, so I talked about the modulation speed of LEDs. Relaxation time of the LEDs is fairly low. I have the trichromatic LEDs limited to about 20 megahertz, while the phosphor-based LEDs about 5 megahertz. Now these devices are improving, so these are likely to be conservative numbers, but that's what we have to work with. And so we need to do something to increase the spectral efficiency of our system beyond what the bandwidth will give us. So I promised this huge spectrum, and in fact, if you look at the visible light spectrum, it's enormous compared to Wi-Fi, but we can't really access it directly so easily. Okay? All right, so let's talk about modulation. Now we understand the channel. Again, we're not significantly SNR limited. Okay, so it's mostly these effects of the rise time of the LED and the multipath nature of the indoor channel. So let's think about, when we think about modulation, we'll think about an LED, right? So it's a non-coherent optical source, so I can only modulate its intensity. So it's intensity modulation, direct detection is what we're looking at. So there's two types of modulations that are considered. One is pulse-based, okay? Pulse-based, very simple, right? Very well suited to LEDs, because LED devices, when you look at the power input current relation, is quite nonlinear. So when we have a pulse-based system, then we don't care about the nonlinearity. Okay, and it's low spectral efficiency, so we're going to have to do something to fix that. Okay, so example PPM. PPM has been used in optical communication forever, and that's a pulse-based system. When we're going to talk more about PPM, but let's just say that there is an IEEE standard for visible light communication, and it uses a variant of PPM. So it's a variable with PPM. That's what's in the current standard. So other people have looked at subcarrier-based techniques. So subcarrier-based techniques tend to be more complex. They are not so well suited to LEDs because of the nonlinearity of the LED, but they tend to have much higher spectral efficiency. So that's something to think about when we compare. An example is OFDM has been proposed for this application, and it's actually been implemented in a current point-to-point product, not a diffuse link, but a point-to-point product. I can give you more information if you're interested. Now, smiley face means good. We're going to think about pulsed-based modulation in this talk. So what is PPM? So PPM is when you take your symbol period, it's your symbol time, and you divide it into, say, Q equal time slots, and you send a pulse in one of the Q time slots. That's PPM. So the advantages are that it can be implemented incoherently, and it allows for a very simple transmitter-receive structure. Why do we care about simple structure? Remember, we're trying to put this receiver in a tiny little dongle that hooks at the end of our phone, okay? So we don't want a box, and when this product here is big. It's not on a dongle, okay? So that's what we're trying to do. So PPM has disadvantages, and that's what we're going to address then in our work is some of these disadvantages. The low spectral efficiency, that's a killer. And it tends to have low energy efficiency when you consider peak power limited devices. So what do we mean by that? When I buy an LED, okay, I have a device that can transmit a maximum of, say, 20 milliwatts. And that's what it can transmit. That's it. Okay? So I have a peak power limited device, so I have to work within that peak power limit to arbitrarily say I'm going to change the average power and let the peak power increase is not realistic in these systems. So let's talk about capacity for a minute. Really, I promise, only for a minute. I've tried to eliminate every equation, so I didn't even have a capacity equation in here. So let's think about capacity, and let's think about dimming. What is dimming? Well, I have a peak power limited system, right? And I want to dim. That means that I want to lower the average power. And so I can think about dimming as changing what we call the peak to average power ratio, right? The PAPR. Okay? So the peak power is the LED limit. The average power is set by the dimming. Peak power limit over average is the PAPR. Channel capacity decreases with PAPR. So we need modulations that are well suited to that PAPR and try to get as close to capacity as we can for that PAPR. Okay? So I have a system that looks, I have a criterion that has two components, energy usage, okay, and spectral efficiency. So those are my two coordinates, and I'm going to use this type of cartoon several times during my talk. So let's keep in mind the horizontal axis is energy usage, and left is good. I'm left-handed. Left is always good. Okay, and I want to go up towards spectral efficiency towards my smiley face there. Okay, so that's what I'm going to aim at doing. All right, so we want to improve upon PPM. So first, let's deal with the low energy efficiency, and that's going to be our technique 1. And then we're going to introduce another technique to help with the spectral efficiency. So we pose the following problem. Given I have Q time slots, what is the best signal constellation that I can send if I have a pulse-based system? Okay? So the solution to that turned out to be simple when we consider cyclic codes. Why do we want cyclic codes? Because we want to have very simple devices, and cyclic constellations give us the possibility to design very simple receivers, transmitters and receivers. So when I pose this optimization problem, the answer turns out to be a very well-known mathematical structure called balanced incomplete block designs, BIBDs. And so we had to give it a name, and BIBD PPM turned out to be kind of long, so we said let's just call it expurgated PPM, EPPM, because we're taking, it's equivalent to taking the best codes out of a multi-pulse PPM sequence. Okay? So when you look at the difference, then this is PPM, where I'm sending one pulse, just one pulse out of the queue for each constellation point, and here I'm sending multiple. Okay? But not just any multiple pulses, specific pulses. And notice these are all cyclic shifts of one another, so I've satisfied my requirement. Okay? So we'll see a lot about PPM in the next few slides. Low spectral efficiency, we're going to deal with it later. Okay, so this is that same cartoon. Spectral efficiency, I want to go up. Energy usage, I want to go to the left. So EPPM does that for me. It takes what PPM did, and for the same spectral efficiency, I can have better energy efficiency for peak power limited system. All right. So let's look at complexity. Since I promised that my system can do low complexity so I can have that broad connectivity that I want, let's look at how we're going to implement our receiver. It turns out that the correlation receiver is optimal both in the Gaussian case and in the Poisson case. Oh, I have one equation I forgot to take out. Okay, so ignore the equation. All right, no need to think about the equation. Here's my constellation. This is my signal coming in. Okay, I have a signal coming in. I'm going to feed it to this shift register. I'm going to slide the shift register Q times around, and I'm going to create a vector of output samples that do this linear combination here of those samples of that shift register. Okay, so that's a simple implementation that takes these code words, and I don't have to match to the code words directly. I can do this cyclic detector, and it creates from this PPM. Ha! Magical? Almost. So decision rule is very easy. It's the same as PPM, right? Because you're taking the maximum of each of the energy received in each of these slots after this cyclic detector. Oh, but the advantage is that I have here k times the energy per symbol than I did in PPM. Because for peak power limited system, I have now 3 pulses, so I have 3 times the energy than I would have if I'd used PPM, right? But my minimum distance is the same, is improved. Okay, so here instead of using a cartoon, I'm actually going to show you real numbers. So that's the same as that cartoon, except that I have units, okay? And so what I have here is peak SNR, okay? And I have spectral efficiency in bits per second per hertz. And this is PPM. As I increase Q, my spectral efficiency decreases and my energy efficiency decreases when I'm peak power limited. Why would I ever do that? Well, okay. So what I do get with EPPM is that as I increase Q, my spectral efficiency, of course, decreases, but my energy efficiency continues to increase. All right? So this is good. So I can compare point to point here. It's the same Q, so you can look across. There's on-off keying. So at this point, you should be thinking, she's an idiot. She should just be using on-off keying. Look at the spectral efficiency of on-off keying. We can't use on-off keying. Why? Flicker. You can't use on-off keying because of flicker. You have to put a code. If you're going to use on-off keying, you have to use some line code to avoid cases where you have bunches of zeros followed by bunches of 1 that's going to cause this flicker. Okay? So I have it there just for reference. We don't use on-off keying for visible light communications. All right, so let's talk some more about dimming, because dimming is very exciting. You control the PAPR. So this is very difficult to do with OFDM, but it's very simple to do really with pulse-based modulations. You can either vary the pulse width, all right, to diminish the light, or you can, what we suggest here is use a different code. So by using a different code, by switching from one code to the other, which is done very quickly in software, you can establish different levels of PAPR, different peak to average power ratios. This is a table where you have lots of different BIBD codes from which you can select the one that gives you the PAPR that you want. But in fact, we don't want 100 dimming levels. Maybe 4 or 6 is enough, and then you just need a few codes to get the dimming levels that you're looking for. All right, so here's a very busy plot, but I'm going to point you to the numbers of interest. These two lines here are PAPR 1/2 and 1/4, 1/8, and this is the difference in performance, either horizontally in power or vertically in BR, between ePPM and PPM. So PPM, in fact, does, from an energy efficiency point of view, with peak power limit, it does better than PPM. Okay, so let's solve the spectral efficiency problem, okay? Because that's key. Why is that key? Remember those LEDs, what, 20 megahertz? You gotta be kidding, right? So we need to do something to increase the spectral efficiency so we can use these devices for useful indoor communications and compete with current systems. So I want you to look for a second at these devices. These are standard LED lights, lamps. What we notice about them is that there are really many LEDs on these. So that's what we're going to use. We're going to increase the data rate. We need another dimension. We don't have the flexibility of saying, oh, QAM. You know, I don't have QAM. I can't do PAM, remember? PAM is just as bad as on-off keying in terms of flicker, right? So I got to do something else. So what I'm going to do is use multi-level symbols, but with my ePPM code. So this is what I'm going to do. I'm going to feed each one of these LEDs a different code, or say a subset of those LEDs a different code, and create multi-level. So if I have 3 of these LEDs and they send these 3 codes, I create a multi-level symbol. And by doing this, I increase the size of my constellation, right? And so I increase my spectral efficiency. Okay. I can keep the receiver exactly the same complexity as before, because now instead of having a single peak, a single pulse at the output of my correlator, I have multiple pulses, and I just pick the ones that identify the symbol, right? They're very simple. So I'm very happy here. My happy face is happy that I've moved over this way, and now I've moved up. But that's, of course, just a cartoon. Let's look at the performance that we really get using this technique. This is the plot I showed you with PPM and ePPM way down there. Okay, this is on-off keying, just for reference. This is 3 PAM, 4 PAM, and 5 PAM. Okay, pulse amplitude modulation. Can't do QAM, have to do perhaps PAM. But again, can't do PAM either because of flicker. And this is, for one example, what happens when I change all the other parameters being the same when I change Q. If I change the other parameters too, I can get different lines that go arbitrarily high. But I need large Qs, large number of pulses K for that to happen, and a large number of levels. Okay. Now remember, I have these nonlinear devices. At this point you're saying, well, if you've got nonlinear devices, you don't want a multi-level. But I'm not obtaining my multi-level by taking each nonlinear LED and asking it to create multiple levels. I wouldn't want to do that. For one thing, they age. The values you get today and tomorrow are not going to be the same. So what I'm doing is creating multiple levels by using sets of LEDs, each of them that transmit some of the pulses. All right. So let's see what happens when I put this fancy new modulation through a dispersive channel, because that's what we have. All right, so here I have my pulse. I'm going to put it through the dispersive channel, and this is what I get. So this is a cartoon, clearly. So the output of the dispersive channel looks like this, and what happens is I get these tails that overlap with the pulses. This is a bad thing, and it's especially bad because they belong to the same symbols. All the blue ones belong to one symbol, and all the red ones belong to another symbol. This is a bad thing. So if I have an ideal case, then I get this ideal output. But if I have a non-ideal case, through my correlation receiver, I get these shoulders that diminish my minimum distance, my distance between one symbol and the other, and that's a bad thing. This is a consequence, a natural consequence, the fact that I, on purpose, picked cyclic symbols, cyclically related symbols. If I had non-cyclic symbols, things would be much better. Why? Because each of these little tails, all of the intersymbol interference would all be spread out amongst all of the other symbols, and then they wouldn't accumulate so badly as in this case. So that's what we're going to do, is we're going to solve this problem by making it look non-cyclic. So if I have a non-cyclic symbol, then what I get is all of this interference here spread out amongst all of the other symbols. My minimum distance is decreased, but not significantly. Of course, it depends on Q, right? Okay, so I'm going to make a cyclic symbol look non-cyclic by using an interleaver. I put an interleaver right between the encoder and after the channel I de-interleave. So from the channel's point of view, it's non-cyclic. And I can play around with permutation matrices, and if you're interested, you can look at the paper for permutation matrices. And this is an idea of the kind of gains you can get. So these arrows indicate the improved bit error rate as a function. Remember that sigma? I told you, remember sigma. So that's the width of the multipath effect. Okay? So as the multipath effect gets worse, of course, my bit error rate goes up. And this is the difference between without interleaver to with interleaver for different cases. And these two lines here are theoretical lower bound for the ideal interleaver, if there was such a thing. Okay? All right, so one problem solved. We have solved the problem then for what happens with this multipath channel, but we still have the problem of what happens with the band-limited sources. So what we're going to do for band-limited sources is very simple. We're just going to let them be band-limited. We're just going to let the pulses be as narrow as they know how to be. Okay? So they'll overlap many chip time. Okay? So a pulse that we designed to be like this might end up looking like that. And so if I want 3 of these, what I'm going to do is send the 3 to different LEDs so that I have a true superposition of the power from those 3 pulses. Okay? And if I do this, then I get this kind of performance where I have 2 axes here. This is the relative bit rate. So that's the spectral efficiency improvement, if you will. Right? So this is bit rate over the rise time of the LED. And this is the bit error rate. So red is the bit error rate that decreases as I increase the overlapping length. Okay? So I picked just 50 just as a number. I can maintain my bit error rate below 10 to minus 4. And I have 3 times increase in the bit rate for compared to the limit for the rise time. Right? So if I had a 20 megahertz LED, I can send 60 say, megabits per second. And now I have the spectral efficiency, if you recall, for my, let's see, where is it? Here. So I have, see this line at 1.8 for my modulation, and I have 3 colors of my LED. I can get on the order of 350 megabits per second from this LED. Okay. So, all right. So that explains how we're going to do single user communications. But in fact, the real beauty of visible light communications is the possibility of reuse. Because if someone is using this light here, somebody in the other end of the room can be using another light, right? So they don't really compete with each other. So we need to have mechanisms by which to do this. So here are a few examples of where multi-user really is the name of the game. I have the auditorium that we talked about. Here's a fancy hotel. Here's a shopping mall. I think a library, yeah? So these are environments where people need wireless connectivity, and many people need wireless connectivity. And Wi-Fi fails in these environments. Okay, so what we're going to do is we're going to have superposition of 2 complementary ideas. Each LED then is going to use CDMA, or you could use TDMA, but we like CDMA. We're going to use CDMA, and then we're going to use space division multiplexing. So the different areas of the room get served by different luminaries. But we want to maintain all of the beautiful properties of the single user system, so we're going to use our MEPPM, multi-level EPPM. So there's 2 algorithms that we came up with for doing this. One is coded MEPPM that uses a combination of EPPM and optical orthogonal codes. Okay? So when you're doing the optical orthogonal codes in code domain. All right? So don't want to go over too many of the details here. I can point you to the papers. Or divided MEPPM, where you're taking different code words in the original EPPM and you assign them to different users. Right? So you have different properties for each of these. You have a larger Euclidean distance with coded than with divided, but you have low multiple axis interference with divided and higher with coded. And with divided EPPM, you can support unequal data rates for different users, which is important. So how do they perform? Well, this is the results for multiple power level for the 2 techniques. What I want to point out here is look at 10 to the minus 4, since we took it as our benchmark. All right, so I can support 5, 6, maybe 8 users, depending on the power level that I have. That's not enough. How many of you in here? I need more than that. So to do that, what I'm going to do is superimpose with my CDMA, I'm going to use space division multiplexing. And the idea here is that each lamp is shining a beam in a particular direction with a beam width of, say, 30 degrees. Something on that order for an LED. Okay? So there's no point if an LED on this luminary is pointing in this direction that it should carry the code for somebody who's in the back of the room. That would be silly, right? So let's do this. Let's use some of the ideas in MIMO, since we have multiple transmitters here. In fact, how many? So in our simulation, in our numerical results, we use 25 LEDs per luminary, 4 luminaries in the room. That's actually small compared to what you would have. But that's what we can think about, this large number of sources. And so what we did, and I want to point out that these are recent results actually to be submitted. So this is hot off the press. So what we did is to frame the following problem statement. Say, let's optimize for each LED the transmit power for each user, right? And the receive filter for that CDMA code, right, considering the interference. Use as an optimization criterion, you could use anything. We decided to use max, min, SI, and R, and then impose constraints. Well, what are constraints? Well, there's two constraints. One is max power. Each LED has a max power. We've dealt with peak power constraints all along. And the other is uniform lighting. So we need those two. And so what do we get? So this is the illumination in a 5 meter by 5 meter by 3 meter room, okay? And down here you see a contour plot. Those are the 4 luminaries, and this is contour plot that matches this. And this is what you get when all of the LEDs are on. This is your illumination when all the LEDs are on. So when you solve the problem and you have 4 users, and these little spots here are the 4 users, and this shows where the light is being used for communication in that room for those 4 users. Based on this configuration, 25 LEDs per lamp, then the lamp looks like this. Yeah? So it's just a circular lamp like that. And this is an extreme case where there's one user off to a corner and showing what LEDs are being used for that user. The other LEDs, of course, are being used for illumination. Right? They're not being used for communication. All right. So let me conclude. So what did we do? We said, let's use the lighting system for communication, and then we outlined what are some of the advantages, but then what are some of the challenges. So we proposed applying combinatorial design to this problem to address some of those issues, keeping the system as simple as possible. So proposed 2 techniques, EPPM and MEPPM, multipath EPPM, to address these problems. We looked at overlapping pulses and interleaving to solve some of our bandwidth challenges. And we proposed multiple access techniques so that we can service many people in the same environment using visible light communication. So let's go through our checklist here and make sure that we've actually addressed everything that we wanted to address. So let's say that I promised I would do in maybe a little over 30 minutes. Okay, so low rise times, we dealt with that. We're able to increase the throughput in spite of the low rise times. Connectivity, we kept the modulation and demodulation very simple. Multi-user support, clearly we did that. Dimming, we're able to handle dimming. Shadowing, didn't show specifically, but you can transition from the main part of the impulse response to secondary impulse response instantly. It doesn't have a problem with that. And we were, of course, not sensitive to flicker. So that concludes my presentation. I'll leave you with a biblical quote, and I will take questions.